you very much. Welcome back to everyone for the mid session, I must say. And here we have the speaker, Dr. Chirodeep Bakli from IIT Kharagpur. So let me introduce him in a formal way. So Dr. Bakli is an assistant professor of energy and science engineering at IIT Kharagpur. He has completed his BTech and PhD both from IIT, but it's IIT Kharagpur itself, sorry, and served 2 years as assistant professor in IIT Ropar before joining the IIT Kharagpur. His research interest is in microfluidics, nanofluidics, interfacial phenomena, molecular dynamics, renewable energy, thermal and fluid sciences, and for building energies. And his research focuses on multi-phase fluid flow and heat transfer with the twin objectives to understand the interfacial interaction and flow physics, and aim to utilize the same to develop smart surfaces and for renewable energy generations. I hope that I have read out everything correctly. And now I'm handing over the session to Dr. Chirodeep. Over to you, sir. You can share your screen and you can start your presentation. Thank you very much.
Good morning, good afternoon to all. Please do let me know if my screen is visible and if it has gone into full screen.
Yes, it's visible. Yes, sure.
It's perfect.
Fine.
Just to confirm, is it fine, Chirodeep, if we record and use it later on our YouTube page to upload?
Sure.
Okay.
I've tried to keep all the images and stuff, free from copyright. But then again, I am not the one who would go to jail. You are going to upload.
Okay, thank you.
So, I audible properly, right?
Yes, you are properly audible.
Okay, thank you. So let me start with the top. So I have tried to keep the top less technical, more of interactive, because hybrid sessions, I see some people are attending it from lecture halls. A lot of people are online. So they tend to get a little boring because it is always one way passing of information. But so I've tried to keep it interactive, but interaction in this hybrid mode is difficult. But please feel free to shout out, stop me, type something in the chat box, because I have two systems. I can see the chat box and the cameras from the other side. So I keep on looking here and there. So that's why you can see my face rotating. But yeah. So when I was invited to this talk, I saw their brochure. It was Applied Mathematics Symposium. And at that point onwards, it was clear that obviously I know the organizers, and hence they have invited me, because I do not know much about mathematics. I'm not a mathematician. So I would at the very beginning like to apologize to all the mathematicians who are forced to sit through it. But so I should thank the organizers, Professor Mukhopadhyay, Professor Pramanik, and Professor Vikas from the individual institutes to invite me to this forum and give me this opportunity to interact with mathematics and make a fool of myself. So let us begin. I would begin with my experience this morning. I was going through the website and I saw my abstract is looking really nice with things that I do not know about. So I called up my friend Shotyajit, okay, because of whom I am in this year, and we saw that my abstract has swapped. But that had something good to do with it. In that break between Shotyajit replying to me and I tried to look into other things about artificial intelligence and machine learning, and that really opened my eyes. So. So I would like to begin this talk with a quote from Professor Steve Brunton from University of Washington, from the same university our plenary talk was about to be. So he, in one of his YouTube videos, starts with "Hello, time travelers from future," and his logic is that the field of artificial intelligence is progressing at such a fast pace that, anything you talk about artificial intelligence might, change in the order of days, minutes, or even smaller than that, time scale smaller than that. So, it becomes quite redundant to come up with theories and, boast about them. So, I would like to give him a nod, like that really, all YouTube videos technically we are seeing somewhere in the future, but yeah, that was something, sort of inception level sort of thing, if I want to say. And, you know, and that made me thinking like how AI is, always playing with us. For example, I was trying to get an image of Professor Steve Brunton and also ensure that is free from copyright. Then the moment I started typing Steve, the AI made me type Steve Burton. And I saw that that's an actor. Okay. And for a moment, I was very confused. And then, we got back and it took time. So, use of AI is typically can work in both ways, and especially when it is, in the field of mathematics. And hence again, I would like to give another quote from his YouTube lecture where he portrays the Starry Night. So, this is the famous painting from Van Gogh. And then again, it is, augmented with AI. So you can actually see stuff moving. And so basically, these are nothing but carefully curated flow profiles, which, give you the feel of the Starry Night by Van Gogh. So I was really mesmerized to look at this lecture, and I wanted to use this in my slide. So I thought of, quickly mailing him, and I was wondering that I do not have much time. So would I get a confirmation? But then I started looking into the website, and I saw that AI does actually have a lot of stuff in the free domain, copyright free domain, and not only Starry Night, they have gone to a total different level with Starry Night. So, and that, I was going through the other lectures, and that made me wonder what AI can do in the field of fluid mechanics, which is so much of mathematical, actually a lot. So if we consider macroscopic fluid mechanics, it can control fluid, it can forecast and predict behavior. It can, replicate large-scale real-life scenarios, for example, ship sailing on the ocean, aircraft flying, into in silico experiments, which can be done on computers. Any person sitting with a computer terminal, a laptop, or a smartphone can actually do stuff which required, huge water tanks or wind tunnels in the past. So, AI has, I know you have heard it for umpteenth number of times, but technically AI has revolutionized everything. And especially when I see something which is not related to my field, AI can deal with turbulence, which, as someone who is not very strong in mathematics, always uh, that remains an area of, dispute. And that can, do some real good to the people, that is part control, so water flow measurements and etc., which otherwise is very difficult to manage with the traditional techniques. And with that, if you see the weather predictions and all, they have gotten really, really very appropriate with time. And that makes me to quote something from my mathematics teacher. And since we are doing a copyright thing, I would like to give her picture. So she's a mathematics professor from IIT Kharagpur, and I love her quote for her. She says that I can peacefully sleep at night knowing that the next morning I'm fighting with equations and numbers and not with people. So, AI helps us to deal with these numbers and equations. So AI has made our life a lot simpler. So now that brings us back to my field of research, which is, AI for low Reynolds number hydrodynamics, which Professor Mukhopadhyay was earlier pointing out, that thin films often transition into turbulence irrespective of the Reynolds number not being quote unquote turbulent. So does AI actually have a role to play with it? Because with low Reynolds number, we really reduce our PDE into a simple ODE, and then we can solve it simply. The non-linearity is gone, not ODE actually. The non-linearity is gone, and we can solve it simply. So what does AI has in store for low Reynolds number? So I'm a person talking about confinement. The topic of the lecture is confinement, and we would try to focus. But before we move on to that, let us have one slide for the people who are very sleepy. So, AI and mathematics and fluid mechanics integrating is quite a nice thing over there, because people here usually many people have a phobia from mathematics. Okay, so and that's why we love our mathematicians, and there are so many jokes about mathematicians walking into a bar. Okay, because people are somehow scared of mathematicians and numbers. And AI is the stuff that bridges the scare of numbers with normal people. I shouldn't say normal people, people who are who do not know mathematics. So AI has made it very simple for them, and just on a start on a lighter note, I would like to ask the audience, can you have some references of mathematics in pop culture, like mathematics movies? I'm not stopping for you guys to answer it, because it's online mode. So I would go. So there are certain movies, A Beautiful Mind, Nash Equilibrium, right? Good Will Hunting, Hidden Figures, and obviously The Imitation Game. And to cite something from India, of course, our computer lady is Shakuntala. So to keep the mood light, all these are real life stuff. But instead of citing the real life people, John Nash or Alan Turing, I decided to go by the movie posters. But obviously, our Indian computer lady, she needed a special mention, and I decided to have her in the poster. So just let us, for a timing, take a pause and try to imagine what if AI was there at its current form when these events occur. So all these are inspired. All these movies are inspired from real life stories, and what role AI would have played. Actually, if AI was there, these these things would not have existed, because what Shakuntala Devi could recall, do with numbers. AI, now we have finger. I would not say palm top, but probably finger top devices which can do it faster. So that makes AI quite a scare and very interesting. And on that note, I would like you to. I know some of you might have read, but this is not paid promotion, but I got this, copyright-free posters of these two series from somewhere. So, in pop culture, usually mathematics doesn't get the appreciation that it has, even engineers. So, if you come across the series of Chernobyl, which talks about the 1986 disaster in the Soviet Union, the nuclear disaster. So, and how mathematicians and engineers helped to sustain the aftermath. And talking about today, power system management is something which is much or more or less like a fluid flow. There is a supply, there is a demand, and you need to connect both via power lines, and you need to manage it from tipping, just like flow control. A series, this is a Polish series, the High Water is a Polish series, which, give me a second, I would have the laser pointer so that you can see. High Water is a Polish series which talks about the 1997 Central European flood. And the problems with mathematical modeling that happened with water flow modeling that caused a lot of mismanagement in Poland for the floods. So now, while we give a nod to these movies or series in the past, which had mathematicians and engineers at its core, we also do appreciate that what AI can do for us today. Okay, and how by use of AI, sort of the entire system of mathematics has been democratized, that whether you love numbers or not, you can crunch numbers and you can generate significant data. And that once we have removed turbulence and all this stuff, that brings us to the driving force behind the AI. And that is basically the integrated circuit chips, which have really shrunk all the devices to a scale that huge numbers can be processed in a matter of seconds. And this revolution occurred because of shrinking of transistors, which are basically solid state devices, diodes, transistors, and stuff. And they're shrinking, as you know, the famous Moore's law. I need not quote it. So the number of transistors double and the device size shrinks. So, the transistor itself tends to shrink. But currently we are facing, a barrier on further shrinking the size of the transistor. What is that barrier? The barrier is it the thickness of the transistor cannot go beyond the limit where tunneling effect comes into play. So, all signals are transmitted by current, which is basically flow of electrons. And if I shrink my size of the device or transistor to a level so that a electron can quantum tunnel from, one side, from the drain to the source, that spoils my entire transistor and cannot use the transistor. So what is the way out? The way out is to use a fluidic device. Why fluidic device? Because fluidic devices do not allow electrons to tunnel, because fluids allows ions to pass but blocks the electrons. So if we can manufacture a device with fluid which can pass signal from the source to the drain, we can bias it through an infinitesimally thick reservoir. And towards it, we try to postulate something called a fluidic diode. Now, what is a fluidic diode? Fluidic diode is nothing but a connection of microchannels and nanochannels, which can be used to pass any signals. Okay, so it can be used for any computation in any data process. The essence of fluidic diode, now I'm simplifying it a lot, so in order to take out the electronics and microfluidics out of it and keep it more or less mathematical, so that we can go into the AI stuff. So the crux is that we know that at fluid mechanics is basically, laminar fluid mechanics is nothing but proportionality between the pressure drop and the flow. So we somehow try to tweak it so that, whatever pressure you apply in one direction, it would be linear. In the reverse direction, it won't. Okay, so just like a diode, it allows the current to pass in forward direction, blocks it in the reverse direction. And obviously, to pass the current in a forward direction, we need a threshold voltage. So similar to that, we try to propose a fluidic model. So the essence of this proposal is that, in today's talk, you would hear a lot about fluid mechanics for AI. AI for fluid mechanics. So you can, model flow control, turbulence, flood waters, and all. So this is something like fluid mechanics for AI. You are trying to, repay AI, where, smarter AI devices, smarter technologies can germinate from the field of fluid mechanics, whereby precisely controlling fluid flow, we would be able to tune the flow rates to a level so that it can act as an electronic circuit. Okay, so that brings us to the field of confined fluid with interfaces and without interfaces. So how do you manage the flow of fluids at small scales? Okay, so mathematicians would again say that small scale fluid mechanics is Stokes equation, which is simpler to solve. So but there are certain challenges, and the introductory slides are to address these challenges. So when we talk, so we would address these challenges in two parts: one with confined fluid with interfaces, and other is a continuous flow. Obviously, in both cases, we have interfaces, but here the term interfaces means there's a fluid-fluid interface or a liquid-gas interface. And whenever there is a liquid-gas interface, that is basically, capillary action in place. And we know that when there is a curvature, there's a pressure gradient which allows everything to flow. So we all have seen droplets, films, and other things that helps us to carry a host of phenomena, including capillarity. So this is a high school textbook diagram from capillary motion, and obviously that helps in a lot of real life scenarios. So this is basically a RBC squeezing through a blood capillary. So that blood filtration and capillary motion of blood is basically via capillarity, and hence we call it blood capillaries. Similarly, tall plants, they tend to carry water to tens and hundreds of meters, and that is also the capillarity in the xylem tissues. So whenever we have an interface of a confined fluid, there is capillarity, and that is something interesting. When we have a confined fluid which is flowing, so there are no interfaces, and that obviously brings us to two very famous problems in fluid mechanics: the Hagen-Poiseuille or the plane Poiseuille flow equation and the Couette. So they basically, I am very terrified to explain this to a bunch of mathematicians, but they are lovely because they are the simplest solutions of the Navier-Stokes equation. Okay, and they are analytically solvable. So it is have a parallel plate, apply a pressure gradient, you would obtain a nice parabolic flow profile, which is dealt with two boundary conditions. One is the no penetration boundary condition. That means no cross-axial velocity or vertical velocity in the wall, and no slip, which is the velocity at the wall is equal to the velocity of the fluid next to the wall. So that is the plane Poiseuille flow for you, and Couette flow is the other thing where you are dragging one of the walls with a definite velocity, and that drags the fluid layer next to it with the same velocity, and hence you get a linear flow. So these are the two simplest solutions of the celebrated Navier-Stokes equation, which uh, which sort of defines a paradigm in fluid mechanics. But there is there are certain issues to this equation. So, for example, I'm dealing with a pipe or parallel plates made of aluminium or made of copper, made of glass. The equation doesn't change; it remains the same. Uh, so the basic essence of this equation is that I do not take into account the material property of the surface. Okay, but if we just go back and see capillarity, capillarity is all about materials. Uh, Again, middle school stuff. A drop of water would wet a glass slide. A drop of mercury forms a globule, doesn't wet glass. Okay, so that is all about the material. Then again, if you go out, see a tree, a tall tree like banyan or something from the ficus family would have a sort of a xylem structure. Something like eucalyptus, which is taller and leaner, would have a different xylem structure, and a shrub, say a rose or something like that, would have a different xylem structure. So when we talk about fluids of interfaces, it is all about the structure of the interface, but somehow solution of Poiseuille flow and Couette flow doesn't talk about interfaces. So that raises a question: how do we define the boundary conditions, and especially how do we treat the no-slip boundary condition? And in order to answer the validity of no-slip boundary condition, we try to look into the spreading of small volume of liquid onto surface. So it can either form a droplet, a blob, or a film, or something like that. And that totally depends on the type of material. So the interaction energy between a drop of water and the material. And if we again mathematically, since we are in a mathematics forum, mathematically it is given by the Young's equation, which is the balance of the interfacial tensions of the pairwise three-phase. I mean, it's a three-phase contact line, and you take pairwise, and you get the interfacial tension. But if we focus on a small portion of the film or the droplet towards the edge, so we can, without loss of generality, we can assume that's a wedge. And after splashing the volume of liquid onto the surface, this wedge would realign itself. Okay, it would take some time to to react to the interface, and to the interface would tell it, okay, you are a drop of water or you are a drop of mercury, and either I love you or I hate you. So decide what is going to be your configuration. And at that point of time, this wedge would adjust. The adjustment of the wedge would occur via motion of this red colored edge, or where you can see my laser pointer moving. And obviously, this is in strict violation with the mathematical approximation that we have here, that is a no-slip boundary condition. So that raises the question that the no-slip boundary condition is not valid, and uh, the only reason that we use no-slip boundary condition is the assumption that if we have sufficient volume of liquid and sufficient volume of wall, and they interact with each other, they exchange momentum and energy completely. And we believe intuitively that the fluid next to the wall would have same energy as that of the liquid. But as we see with confinement, with small scale, the surface area is much larger than the volume. And when we are talking about a droplet, a film, that is not always true. And that again brings us to the question that is everything laminar or turbulent? That's a macroscopic definition or a microscopic definition? Okay, so we would come back to that later. But turns out that again, mathematics simple here. We cannot forget Navier. Navier himself gave a way out to the situation. Okay, so he postulated that the Navier, same Navier from Navier-Stokes equation. So in 1823, he said that just like the no-slip boundary condition, you can have a slip boundary condition where you draw a tangent to the slip. So at wall, there is a slip velocity. So the liquid is slipping with respect to the wall, and you draw a tangent to that velocity near the wall, and where it meets the zero velocity line, that distance away from the wall is basically measured as the slip length, and that comes as a mathematical boundary condition defining the wall shear stress. So you take the gradient of the velocity, take the slip velocity, and define something as the slip. Now this slip length has been a mainstay of solving the so-called paradox that was done with the edge of the wedge of the fluid, and classically that is called the Hu and Scriven paradox. And not only that, the slip length is a term that we resort to define any type of surface. So if you are trying to define a hydrophobic surface, some variation in viscosity, variation in structuration, we'd always resort to this slip and try to define it in that. But the question remains, how do you define slip actually without going into the molecular structure of it? Because as soon as we are talking about a small fragment of liquid next to the wall, we are beyond the scope of continuum hypothesis. So the our favorite ODEs and PDEs are no longer valid. The rules of differential calculus no longer hold at that point of time. And if the fluid is confined to a scale where the slip length and the channel dimensions, they are of the same order, things really become messy. And in that case, to quantify slip, and especially when you are talking about nanofluidics, we need to probe the molecular structure. And that is not easy because, again, the Eulerian framework comes to a halt, and we need to go back to our good old Newton's equation and Newton's laws of motion, and resort to something called molecular dynamic simulations to obtain that trajectory. So this is a mundane routine where you obtain start with the initial configuration, that is the geometry, and decide a potential for it, and then you obtain the force field by a combination of this. From the force field, you obtain accelerations, integrate it to obtain velocities, and integrate it to obtain the positions. You update the positions, you obtain the trajectory, and hence you actually probe into the molecular nature of the system, and you try to do the interface. So that's a bit of description. So I would share the slides so that you can look into it. So how do you describe the potential, especially something for water, which is polar, which has, the oxygen heads, smaller hydrogen heads, polarization and all. So there's an angle and stuff that you learned in chemistry. And if you're not fond of chemistry, probably stuff that you have forgotten. So this is how you start with a small water molecule, and then you try to string the beads together and get the entire system, write a numerical code like this, use a software, and string a trajectory together. Okay, and that is how you obtain the molecular nature of the stuff, and voila, you obtain the slip length. So, this is a typical configuration where you see this yellow stuff is the wall and the stuff inside is the molecules. Okay. You obtain the trajectory, you integrate the velocity profiles and, divide it into bits, and you obtain a scatter, something like this, these blue dots that you see. Now, these blue dots seem to be scattered here and there, but, they have a particular tendency. And if you try to do a curve fitting, you would see you'd regain your parabola. And what is a parabola? Or a parabola is the profile of velocity in a plane Poisson. So this is nothing but you apply a pressure gradient to these molecules move, and they would give you something like a plane Poisson flow equation. Okay, and you see, since we are talking about molecular scale, we extend this velocity, this velocity to the wall, to the zero velocity location, and we obtain something called a slip length. Obviously, this is not the direct definition of the Navier slip, because for Navier slip, I would have needed to define a tangent, which is like this, but this is a direct extension of the velocity. You can define it in your own. So this is, totally artificial, which we try to get out from the dance of the molecules. Okay. So yeah, problem solved. Do molecular dynamics, obtain the A. But is slip that easy to quantify? So basically, it turns out that there can be numerous types. It can be because of mismatch of momentum, mismatch of temperature, mismatch of charge at the interface. Momentum slip is something like the Navier slip boundary condition, which we get. If there's a temperature jump, we use something like a Maxwell model, not discussing here, where you deal with the temperature fluctuations and try to treat it. If there is an ionic jump, obviously the ions from around the from near the wall distribute themselves in the interface, forming something like the Boltzmann distribution or the electric double layer. And this is the equation. Do not care about the equation, but the crux of this is that it tries to every quantity you introduce, it alters the boundary condition. And his definition of the slip is not that easy. Thus, this non-trivial interaction between the ions and something like polar fluid like water is actually very complicated, even if you are trying to solve something as simple as a Stokes equation, because it is not about solving the equation, but actually about specifying the proper boundary conditions. Okay, so, and if we try to look into the conditions that give us these boundary conditions, what are these? This can be the lattice parameter, because you see, at molecular scale, there is no difference between the solid interface and the liquid. They are all molecules. Like, for example, my hand here, the air next to it, you cannot, there is no difference when you come down to molecular scale. Because, molecules, they interact and they have some memory of the stuff they come from. So if it's a solid molecule, they are more closely bound. If it's a liquid or a gas, they are loosely bound, but they are molecules at the end of the day. So how do we actually specify their, affiliation to the molecular, to the structure? So it turns out that, if the molecule is a simple cubic, a face-centered cubic, or a body-centered cubic structure, they would behave differently. How differently, we would discuss it when we come to the AI part. Then again, the liquid molecules next to an interface behave in a different manner. For example, let us take two paradigms. Sorry, is that a question? Okay, sorry. So the liquid molecules next to interface behave differently. For example, next to a hydrophobic wall, the liquid molecules would tend to stay away from the hydrophobic wall, and hydrophobicity would induce fluctuations. These fluctuations would be steep, but would die as we move into the bath. Hydrophilicity would induce steep fluctuations, which would die as we move into the bath. As opposed to it, if we consider hydrophobicity, they induce fluctuations far away from the wall. They are not very steep, and that causes a lot of disturbance into the bulk of the. So, not only the structure of the lattice, but also the chemical property of the lattice would tend to alter how my fluid next to the boundary would be. And if you see the green and the red lines, so there that is the difference of fluctuations on addition of salt. So introduction of ions, makes the things more complicated. And thus, uh, we have lattice structure, wettability, salt, addition of salt, all these parameters deciding how does your molecular structure would be. Now, here is the point where AI comes. So if you are to specify the boundary condition for individual systems, there would be infinite number of systems and umpteen number of parameters which gives us the which would give some change. There would be some interplay, some complex coupling, and thus defining a unique boundary condition, like something like macroscopic property, like surface tension of water, surface tension of alcohol, or viscosity. Slip length doesn't come with that uniform package rating. It depends on the system, and at every time, if we need to run a simulation, that becomes very complicated because this was supposed to run, it is not running. It was a video file. Let me click on it. No, that still doesn't work. So nothing, just molecules moving in a particular direction. It was a fluid flow file. So for each case, I would need to run a molecular simulations. So running a typical molecular simulation for a few nanoseconds is typically a job of days for a supercomputer. And we do not have that much of resources. And there is where we resort to AI to get this molecular signal in a quantized form. So here are some questions. So what is a typical trivial solution to this? See, trajectory files are nothing but ensembles sandwiched upon each other. So we have, say, a million of ensembles, and we look into them, and we try to, basically these are nothing but dance of molecules, and we try to make something out of it. So a trivial solution can be that instead of going for a million of ensembles, I take 1,000 ensembles and try to find out some pattern in that randomness using AI, and then replicate those thousands till they go to a million. Matter of minutes for AI would take days on if you do actual molecular dynamics. So that's the trivial solution of applying AI to molecular dynamics, but there are more sophisticated ways to do it. And in order to understand that, we would take an example where we would deal with flow rate and pressure drop. The laminar linearity between flow rate and pressure drop from continuum, let us try to examine. So what we do, we take all these parameters and try to plot dependence of slip or enhancement factor. So slip length, I have explained, enhancement factor is nothing but the augmentation of flow rate that the slip is causing. Okay, so you can represent it in either way. So how does these depend on the independent variables? So IVs is the independent variables. So whatever you see here in color are the stuff, the independent variables, which can change my enhancement factor or slip length. So they can be viscous interaction, they can be wettability, they can be charge distribution, it can be surface roughness, it can be the lattice structure, it can be the channel dimensions. Okay, these are just to name a few. There can be other millions of stuff. Okay, so what we do, we vary the surface energy and try to see how does the enhancement factor change. So this is what the graph looks like. I do not have any words to explain the graph because this A is pretty random. If I try to make sense out of this randomness, it would take me years to get tangible data out of molecular dynamics. But the savior AI comes in. Okay, so what can we do from AI? Okay, so how would again the interface and the fluid interact with each other? It is via the interaction at the interface. Whenever there is a solid interface and a fluid next to it, or vice versa, a liquid interface and a gas next to it, how does these molecules interact? They interact by fluctuations or random oscillations, which we just saw earlier uh, at the interface. Now, if I can make some sense out of this oscillation, now you can classify them based on wettability, based on interfacial interaction, based on the lattice structure, then I do have a key to characterizing the behavior or the macroscopic property of the system. And towards it, we take the water structuration next to the interface as our key to solving the issue of boundary condition that we introduced earlier. Okay. So what we do, we take, again, our paradigm of a hydrophobic and hydrophilic surface and try to see how, as I was discussing earlier, a hydrophilic surface would have a lot of fluctuations because it is next to the interface. A hydrophobic would have less fluctuations, which would go deeper into the path. Now, I cannot have, the liberty or the leisure to simulate the entire data, but I take a small fraction. And what is that small fraction? It is the two peaks of water density fluctuations, which are just next to the wall. Okay. Yeah, I have, Prasamgod, I have noted that. I would take just 2 minutes to wrap up. So we would take these two peaks next to the OVA and try to make some sense out of these two peaks. Now, the basic essence is that these two peaks would give me some numbers. Okay, the height of crest, the height of trough, the width of crest, and stuff. So, just like plotting a waveform, can I plug in some numbers to replicate this waveform? If that can be done, the reverse can also be done. So with certain numbers, I can actually predict how the waveform next to an interface would look. And towards it, we choose the value of the waveform at certain distances. Now these distances come from some understanding of the molecular phenomena, which we would skip for the time being. But from the AI perspective, we can draw a heat map and how these parameters or the density values at these specific values of distances from the wall, they are related. Now, once that is obtained, we can actually obtain some sense to this data and try to replicate the behavior of this. Okay. Now, using that, we had a recent publication in Journal of Chemical Physics. So this is the excerpt from the publication. So the technical part, you can go ahead and look into the paper. I would share the DOI and stuff. So it is a part of a special collection of Journal of Chemical Physics, that is machine learning with molecular simulations. So yeah, so then we do nothing. The artificial intelligence or AI stuff is not fancy. We typically do a rectified linear unit to connect the IVs and the DVs with hidden layers. And this is typical machine learning thing. And finally, the purpose is to obtain a variable input. So the importance of the acceleration is, or the shear is pretty strong, apart from the density at different points. The channel height doesn't feature a lot because the acceleration of the shear is normalized with it. So based on it, we do two paradigms and show that any flow can be classified as a high shear and a low shear paradigm, and accordingly we can draw a feature importance map where we try to classify these parameters, and that gives us the strength of our model, that without going into molecular simulations, we can, simply see a static scenario with certain density distributions, and use the density fluctuations to decode the molecular behavior and predict how the fluid would behave under dynamical conditions. So that revolutionized the field of microfluidics and microelectronics, as we can tune microelectronic circuits by just altering some fluid parameters. So that is the crux of this EA. Please feel free to read this paper. A lot of stuff is there, but obviously, that would make a online presentation a lot boring. So I have skipped the technical stuff. So I hope that's okay with you. And I have also exceeded my time. I apologize for it. Do I have time for questions?
Yes, sure, no problem. Thank you so much, Dr. Bakli. I would like to request our participants, if you have any questions. For the online participants, please raise your hand. We'll come back. We'll come to you one after another. For the offline participants, if you have any question, please feel free to ask. Do you have any question? Yeah, sure. There is a. Sure. Yes, Shagnik, you can unmute yourself and you can ask questions.
Am I audible?
Yes, you are
Yes.
audible.
Thank you, sir, for this wonderful lecture. I have one question. Like you are saying that to understand this fluid dynamics, we are going into the molecular regime. So we need some kind of quantum mechanics there. So in that case, you said that the distribution is given by Maxwell-Boltzmann distribution, which is a classical distribution. So I think that it should be Fermi-Dirac or Bose-Einstein distribution to understand the fluid.
No. So yeah, see, if we go beyond the classical molecular dynamics, we would need quantum distribution. But the only time I quoted quantum was during this slide, where I said quantum tunneling of electrons. I know nothing more about quantum. Molecular dynamics, we do only classical molecular dynamics, where ion distribution is given by the Boltzmann distribution.
Okay.
And nothing more than that. Okay. So yeah, but a higher order model would be required if we go into quantum. Thank you.
Okay, sir.
Anyone else?
May I ask?
Is there any questions from the offline participants?
May I ask one question? Is it audible?
Yes,
Okay.
you are audible.
Sure.
Yeah, thank you. So in your the AI part, when you started with some data, you are actually showing some pictures. Can you go to that slide?
Here.
Yes.
Here.
No, the one where you were actually showing peaks and you are trying to predict.
Okay. This one?
Yeah. So these datas, where did you get, like
Yeah.
these are experimental data or some
No.
literature data, or you are simulated data?
So I would explain this. So density fluctuation data can be obtained from equilibrium molecular simulations. Equilibrium molecular simulations are lightweight simulations which take far lower time than non-equilibrium simulations. So, and whether the fluid is being sheared or not, so whether it is static or dynamic, the density fluctuation next to the wall would remain same. Okay. So, this is the hangover from the no-slip boundary condition. No-slip boundary condition says that if the wall is stationary, the fluid is stationary next to it. That's not true. We know now. But whether the wall moves, or whether the fluid is moving or not, the density fluctuations is stationary next to the wall. It depends on the viscosity, the wettability, or the physical roughness. Nothing else. If the fluid is moving or not, that is totally independent of it. And hence, that helps us a lot, because just by using the static MD data, we can replicate non-equilibrium molecular data using AI.
Okay, so to understand something in these confined fluids, if I using AI, I should have some confined fluid data either from this molecular dynamics simulation or experimental data, and then go from there to determine something more complicated, which is possibly difficult from your MD simulations or something like that.
Yes, yes. Unfortunately, that's the bottleneck. The starting point. It requires some experimental or MD data for a static system.
Okay.
For the
Yeah, thank you.
particular
And yeah, thank you. One more question. When you are showing this histogram thing, I just want to confirm what is A representing in your.
Acha, A is the shear. A is acceleration basically, which is the molecular scale derivative of the pressure. So pressure divided by volume would give you acceleration. So typically in molecular dynamics, we quantify pressure using acceleration.
Okay.
So that is where
Thank
we
you.
segregate dynamics and statics.
Thank you.
Is there any other questions?
I think Francesco has.
Yes, yes.
Yeah, hello. Can you hear me?
Yes,
Yeah,
I
yeah.
can.
Sure.
Okay. So thank you for the very interesting talk. Actually, I had a question regarding matching the molecular dynamics with a continuum mechanics, basically creating a macroscopic model for the slip condition, basically. So, what is the characteristic scale at which you need to use your ensemble for the AI in order to predict the model? Because I mean, close to the wall, it's well known that molecular dynamics gives fluctuations of density, and actually it's also a case for viscosity. So what is the scale that we can that we should assume to get?
Yes.
Okay.
Yeah, that's a great question actually. So that brings us to the applicability of the range of scales. So obviously, the breakdown of continuum and switching to molecular dynamics, that would be decided from the Knudsen number. But once we are beyond it, we use the height of the channel itself as an input parameter for our machine learning algorithm, so that we ensure that these statistical fluctuations, which might be a artifact of molecular simulations, that do not come into play. So we get a beautiful continuous profile as we start from say about 3 nanometers, which is 10 times the diameter of 10 times the size of a water molecule, up to somewhere about 30 nanometers, beyond which again some sort of modified continuum again kicks in back. Okay, or the range of applicability of the molecular dynamics. So yeah, we have tried to keep the profile continuous and have several cross checks in order to see that statistical fluctuations do not influence our results. I hope that answers your question.
Yeah, yes. This, but how? But this changed also, I think, when we want to include an interface, right? Because normally density fluctuations near the wall, they are about order of 20 angstrom and so on, but the Laplace equation is somehow violated up to 100 angstrom. So it's this estimate is gonna be readapted if we have like a liquid droplet that's sliding on a wall, right?
Exactly. So the results that I show are for a flow which doesn't have an interface. I mean, it's a continuous flow. If we go into, so there is total another study on that. Probably if we have some time to interact, we can go there. So if we go back to liquid droplets, discrete droplets, capillarity, that totally would violate this. Okay, so a case of a Young's equation, which has a far larger scale of A, there we cannot use a simple MD simulations and fluctuations to predict the equations. It talks about systems which are, plane causal and fluid.
Okay, thank you.
Okay, so is there anyone else to ask a question to our expert? If it is not the case, then we would like to say thank you to Dr. Chirodeep Bakli for accepting our invitation and for such a wonderful talk. I'm sure if any of our participants has any question, they can let us know in the chat box, or they can directly contact to you for the later conversation. So thank you very much once again.